continuum of behavior here. So this is like, this to me is like a really impressive demonstration of the power of SED model.
How is the mass estimated?
In this case, I believe it's inferred from the rest near IR fitted to stellar SEDs. So if you take points along the main sequence here, and you redshift them back to 0, and you normalize them to the same star formation rate, you get a distribution like this. And if you take the points that are the starburst and you do the same thing, you get a distribution like this. And you can see that the main sequence galaxies have a thermal far IR distribution that's cooler with more PA emission than the starburst galaxies. So I thought that was pretty impressive. So we tried to do something like that ourselves with some of Giovanni's GTO time on Spitzer, where we took a sample of nearby galaxies that we had constructed to be representative of star formation in the local universe, and we observed them with Spitzer at 8 microns. And we inferred with the Spitzer observations, the total masses and the total star formation rates, and that gave us a plot like this. So we're trying to copy we're trying to follow in the footsteps of Elbaz et al. And we actually get a very similar slope and distribution. We can reproduce the star formation main sequence that way. If we look at if we put an aperture down just over the nuclei though, we get a different slope. We get kind of a different behavior, which looks like the star formation is mostly concentrated in the nuclei for the lower luminosity galaxies, the lower mass galaxies, which was kind of interesting.
Is that a fixed width aperture?
I don't remember if it was fixed width. These galaxies are all IRAS galaxies, so they do occupy a range of redshifts, but they're all relatively local. I would have to check that.
It's fixed 2 kiloparsecs.
But we tried to do that. We tried to break that down into finer scales to see how far we could push that, and that's what this is. So in these 3 panels, all the blue points are subregions within these star-forming galaxies, and the colored points are different subsets. So the red points are just the nuclei. The green points in the middle panel are the brightest star-forming region off the nuclei, and these orange points are like some random off-nucleus region. And the point of this is that although there are some variations in the slope and the scatter, by and large, if we're using the 8 micron pi emission as the star formation rate indicator, no matter what region we pick, we get about the same slope and about the same scatter, no matter where in the galaxy we look. There's some variations, but it's mostly the same everywhere. Okay. Oh, and I meant to mention, that we did try to do this on a finer scale, but we just couldn't make sense of the results. Okay. So here's Chris Hayward again. In this case, we're looking at just the M3 galaxy again, but from 3 camera angles, and just 1 snapshot in time now. So it's a simulated galaxy at one moment in time, but the point of this paper is that he's going to pixelate it at very fine, from scales that are very fine, 0.2 kiloparsecs, all the way up to 50 kiloparsecs, and see how well he can reproduce the properties of this galaxy that he a priori knows to be true. And I just tried to succinctly summarize those here. I think these one-word summaries do kind of reflect what Chris thinks. In terms of the mass, you can do a pretty good job, even on the finest scales. I don't know if you can see, but the top row there is the 0.2 kiloparsecs. So even if you've been down to very, very fine scales, you can still extract the mass very, very accurately, even for something tenuous like the dust. But you can't really do such a good job for the star formation rate.
Wait, why would you get building in the dust rate and not the star formation rate?
Because they come from, you're looking at different parts of the, you're looking at different wave bands. This is the thermal far IR.
What's he using to get dust?
This would be the mid IR. I mean, I can check. So physically, this is why this happens. The initial mass function is just really steeply sloped. So when you are pushing down to small star formation rates, you get a lot of stochastic effects at the high mass end, and that's what drives the UV radiation, and that's what drives the inferred star formation rates. So if you're looking at something like my favorite galaxy, NGC 1300, and you're looking at a big chunk of it that's 10 kiloparsecs across, you're averaging over all kinds of physical conditions, and you can do a good job of approximating what's there. And you can even do a pretty good job at 1 kiloparsec, but if you get smaller than that, you can tell by eye, you're not going to get too many of these star formation regions in there, and the stochastics inherent in this initial mass function are going to really hurt your ability to pull out an accurate measure of the star formation rate there. And that plays into your knowledge of the star formation history, but you probably can get a good measure of the masses. Okay. Oh, and just incidentally, this is the pixel size of the Spherix mission on this galaxy. So Spherix, which was just approved last week, will essentially be like an IFU at this kind of spatial resolution for a galaxy like this. Okay.
So we've talked a little bit about how it's difficult to interpret the infrared luminosity in various different ways, and how we struggle to connect the infrared luminosity back to the properties of the stars. And remember, we're basically trying to only measure the infrared luminosity. I'm going to talk for a couple of slides here about how it's hard to just measure the IR luminosity, and this is for different reasons. And basically it's because IR SEDs don't all look the same. And only in the local universe really do you have multiple points of measurement here. At higher redshifts, you're kind of lucky to have one. And so the game is, if you have one measurement, usually in the mid-infrared, how can we then estimate the whole thing? And this is a very dangerous game to play. So dust emission, there's a couple different things controlling the shape of the IR SED. The main one is the distribution of dust temperatures here. So you can model this as a single temperature kind of thing, where all the dust has one temperature. Or you can use some physical model for how you think the dust is distributed throughout the galaxy, and then how the starlight is incident on that dust, the intensity of the starlight. So for example, the Drain and Lee model has a couple of parameters here. One, assuming most stars are exposed to a simple interstellar radiation field, which is very low intensity. And so one parameter controls the intensity of that field. And then the other parameter controls how many stars are exposed to very high intensity fields, so how much hot dust emission there is. And you can see that variation here. So there's a couple different models you can fit here. PAH emission, polycyclic aromatic hydrocarbon. So this is kind of a nasty business. The mid-infrared, which is where most of our data comes from at high redshift, unfortunately, this has significant PAH emission. And so this PAH emission has, in the theoretical interpretation, like the way you try to explain it if you start writing it down by hand, it has these complex dependencies on these things that are basically unknown from galaxy to galaxy, like the dust composition and the distribution of starlight intensities. And so these complex dependencies mean if you look at the PAH emission on a galaxy by galaxy basis, it changes quite a bit. So here's two different spectra, pretty straightforward. In the mid-infrared region, you see these whopping PAH emission features, and not only do they show significant changing between galaxies, but you also see significant change within a galaxy, not just at the amount of PAHs, but also the line ratios of PAHs. So this is kind of a jungle out there. The current models are sort of half theory, half calibration, and so when you're applying these models which are calibrated on galaxies, which are often local, to galaxies where there is much less calibration, often in the distant universe, they're subject to significant uncertainties. And so there are limited ways to check these models at high redshift. So you can use Herschel. So Herschel briefly looked at high redshift galaxies. And so this is sort of the selection limit of, this is Elbaz et al. Again, which was mentioned earlier. The selection limit here is roughly in red, of where Herschel can see out to which redshift. And so as you see, as we go farther and farther out in redshift, Herschel is looking at only at brighter and brighter and brighter galaxies. So our selection becomes more biased. And people measure this interesting quantity